Hi, this is Jeff from the Ozark Mountains in Missouri, USA. Well, we're back for part 2 on our TI TMS 990 WAC 189 development board. In the beginning of the first part, I said that, oh, this is like the processor used on the TI 994A, that series, and then I overlaid some text. I said, oh, I was wrong. Well, turns out I was right after all. It reminds me of that saying, I thought I made an error once, but I found out later I was mistaken. So anyhow, yeah, it's just like a cut down version of the 16-bit processor used in the TI 994A. Less pins, less address space, only 1 byte wide data bus, things like that, but kind of the same idea. In this episode, we're going to make a proper power cable, cassette tape cable, get the cassette I/O working, I hope, and then we'll have a look at the serial port over here to see if we can get that working. And then we're going to try to burn some EPROMs to get rid of this cobbled up mess here that I had to do to get this working, and be able to install UniBASIC on this guy. So let's get started. Thanks to PCBWay for sponsoring this video. They not only do PCBs and flex PCBs, they also have 3D printing service, injection molding service. They do CNC machining, sheet metal fabrication. They also have a thriving maker community where you can share projects and check out what other people are doing. For your next project, head on over to PCBWay. I wanted to get the full cassette interface working on this board. It comes with the parts needed to save and load, but it doesn't have the relay here for automatically controlling the cassette deck. The shape of this relay indicates it's probably a read relay. In the manual, it called it a COSAR 1112-12-1A. Evidently those were made by a company in Texas, and they seem to be unobtainium these days. And to make matters worse, it is a really odd pinout compared to other types of read relays which are in this similar form factor. So I went digging around in my junk box, and I got a relay from a TRS-80 model 102, used for the same purpose, to control the cassette remote. And it was small enough that it would kind of fit in the same footprint, and I added some pins, as a spacer and to connect it. The problem being this is a 5-volt relay, and this was a 12-volt relay. So I calculated the resistance I would need to add in here. You see this little resistor? You might just be able to see it there, that resistor. In series, to run this 12-volt relay off of 5 volts, or 5-volt relay off of 12 volts rather. And then as I got further into this, realizing how this relay was driven, I changed that resistor from 170 ohms to 200 ohms, which brought the current that it drew down from about 42 milliamps to 38 milliamps, which is just under the 40 milliamps that the driver chip for this is rated at. So I had a relay working, and that was good. But for the life of me, I couldn't get the save or load commands to do anything. In the manual, it says, you hit L for load. I'll zoom you in here so you can see the display. Okay, so you can see the display says CPU ready, and I hit L for load, and there was no voltage here where it should have driven the relay coil. Reading through the manual, it also said that this forward LED should have come on, and that wasn't happening. So I reset it, and I tried the dump command, D, which is save to cassette. Again, the display goes blank. Nothing happens. And I got looking through the schematics. I kind of did a deep dive on this. And I found the sheet that shows the control of that output. It has a signal called deck control, which is from sheet 5, which goes in and provides ground to the relay. Okay. And if we go to sheet 5, which is this one, we can see the deck control signal here. It goes through this 7416 driver into a flip-flop, and the output of this flip-flop was not changing. The J and K inputs, which are A0 and A1, they were changing, of course, but the clock or trigger wasn't moving. And I checked all the inputs to this 74LS145, which is a 3 to 8 decoder, and all the inputs seem to work. It does all the other stuff it's supposed to do. And I noticed the outputs which go over to clock this flip-flop are in this wired OR configuration, which is a little odd. And it's pulled up to plus 5 volts through a 1K pull-up, kind of a strong pull-up there. This is a little different configuration. Looked at the data sheet for this chip, and it is an open collector output, so this pull-up in this wired OR configuration is fine. You know, I thought, well, it could be a bad U5 here. It could be I'm not using it right. I'm doing something right. Obviously, when we hit the keys, they are beeping. So it's recognizing the key press. It's outputting to the piezo beeper and everything like that. So I just decided to sleep on it. Don't go crazy pulling chips or hooking up the logic analyzer. Just think about this a little bit. So this morning I read the manual again, and yep, same thing. Forward LED should come on, that type of thing. And then I got to thinking, well, when you're dumping, you have to give it the address and things like that. And when I press D, it just goes blank. That doesn't make any sense. So then I thought, oh, well, I'm in CPU ready mode here. That's just like a splash screen. So when I entered a program, I hit return. That brought up the question mark prompt. Now what happens if I hit dump from here, D? Oh, now it's still up there, and it gives me an opportunity to type in, let's say, a start address, etc. That's what I was doing wrong. So I'll reset this again, and I'm going to hit HIJKL, load, and oops, I did it again. See, from the splash screen, you've got to hit return. Now I can hit load, and you notice that our forward LED indeed come on. So the whole problem was operator error. So it's just kind of a warning. Don't get in too big a hurry to pull up chips and go crazy and go into a deep dive into how the thing works, when the problem just might be that an unfamiliarity with how it operates. So now if I solder the relay board in here, it should work. And we should be able to control the cassette outputs. The connectors for these guys are on the way. I think they're going to show up tomorrow. When those show up, I'll build some proper cables, and we can test out saving and loading programs. Well, to make proper connections to these connectors, we needed mating plugs, and I did find some. Fortunately, in the manual for this, there was part numbers for the original AMP plugs that were compatible with what's on the board here, and I still found those being sold by TE Connectivity on Mauser. So the owner of this board ordered some of those, some pins, and had sent to me. And I already made up a power cable because that was the simplest. This cable's about 12 inches long, which is, I don't know, 300-ish millimeters. It's a 4-conductor cable that's shielded. I'm not using the shield in this instance. 4 wires. Interestingly, in the manual, it shows the original color coding for the various voltages, and I happen to have that on this cable I use. Just kind of, I pulled this cable out of the junk box, and it had the same color, so able to do that. And see, now that plugs in, and we have color codes that match from the factory. Red is 5 volts. That's what it says on the board right there, which you probably can't see. White is plus 12 volts. Green is minus 12 volts. Black is ground. And now we can plug and unplug that just that easy. Also got the mating one here for the cassette. These are polarized. They only plug in one way. And also in the manual, it showed us the pinout for this, which I copied up here. A little bigger, easier for old eyes to see. It's all in one place. You don't have to keep going back and forth between the table and the picture. So now we're going to make this cable. And my idea here for this cable, which might seem a little wacky, is to make a cable like this. Let's whiteify a bit. So we have a cable, it plugs in here, and that runs down to this little box here. And into this little box plugs your regular old vintage cables for remote, earphone, and where's the third one? There it is. Microphone. Like that. And we even have the remote bypass switch, so you can fast forward and rewind the cassette. Put it back into automatic control. These sockets in the switch were all stolen from this junk Sharp CE 150 cassette board. So you can see where the connectors were there. The switch came from the switch panel. I'll take this apart and show you the inside. Well, while I'm taking it apart, you see there's screws on the side here. So this flange piece can slip in and out. So my idea is this could be mounted like on the back of a wooden box. And you can adjust how far it sticks through, however thick the sidewall is. So it's a little over-engineered, but I was just having fun with the 3D printer. So we have a little hole here for our cable to go into. We're using all the same screws everywhere. These are the same screws I used for the CE158X case, so I had them on hand. And we've got a little piece of perf board in here, which was this exact size. The only thing I've done to it is there were holes in the corners, and I just chopped those off like that to provide a little more clearance for the screws. And you can see we've got the connectors and switch on there. Right now, those are just glued into space, or into space. They're just glued into place. I bent down the bottom prongs from the switch through a couple holes on the board. Of course, the connectors to the switch are up here. They're down here for the these connectors for the cable. So this is going to be the trickiest part to wire up, but it just pops in here like this. The cable enters at the bottom right here. So I'll have the cable come in and snake across here like that. Wire in our bypass switch. And Bob's your uncle. The first thing I think I'll do is get the plug on the board, and we'll figure out how to do this part. I've trimmed off about 1.5 inches of insulation from the outer jacket here, which is, I don't know, 38, 40 millimeters, somewhere in there. And I'm going to use the Nipix here to strip the wires. I did a review on these Nipix strippers. They do a really good job on some things, but they do have their shortcomings. And we've got the connectors here, and these are properly sized for this diameter of wire, which is 24 gauge. And I'm using these ratcheting crimpers here. They're not exactly the right ones for this, but they're close enough. They do a decent job. I had to get my old man glasses there. So you want your wire to go through just enough. There we go. The idea with these connectors, if I can get one close here, is that this little wing part back here grips onto the insulation. That provides a strain relief, and the part here in the middle is what clamps around the copper to make an electrical connection. So you want your insulation to go up just about that far. Now, as I said, these aren't exactly the right crimpers for this type of connector. So I've got this set of engineer crimping pliers, and these, whereas, this type of thing has two different steps of crimping in here, this has a bunch of single stage crimping. So it takes longer to do something, but it's a lot more versatile. So I'm just going to go over like that. Give that an extra little crimp, and also on the wire part, go a little tighter there. There we go. Now we have a nice solid connection. And I'll go ahead and do these other 3 wires here, plus we're using the shield as ground, so I have some heat shrink tubing that I will slip over there like that. So I'll get these crimped, and then we'll come back. Got all my wires crimped here, and yes, I already do have my heat shrink tubing there. This is the one little wire with the heat shrink tubing, so it's black like this one's black, but they are different. You can just see maybe right there. The crimp, the first terminal crimped here didn't work out so well on the green wire, so I redid that. So it's nice when you order connectors with terminals, order a few extra terminals, because that can happen. And I added some wire colors here to my bigger picture. So I'm going to start plugging these in here. I've got my connector in position, so I want the green here. Okay. I want the real black wire, not the shield wire. That's this one. I want that there. Okay. Now, the ground, or the common for the audio in and audio out, is either of these two right here. They're both wired together on this plug, so it doesn't matter which we use. We could use separate grounds for that, but there's really no point. So I'm just going to use, let's see what makes the most sense here. I need white and red on this side, so I'm just going to use the middle one right there. Okay. And then I want red. Sometimes if it doesn't want to pop down in there, you can take some pliers or a screwdriver and just gently poke it down in there. And then we'll do white. These big AMP connectors used on here is kind of an interesting choice. I mean, this whole board draws on 5 volts, maybe 7 or 8/10 of an amp. And they use these ginormous connectors, which are probably rated for, 5 amps or more. And then our heat shrink can go down like that. That'll plug in there. We can double check our wiring. We have green, real black, yes. Shield, that's our fake black. Yep, that's our shield. Red and white. Okay. Oh, gosh. Grf. Oh, there we go. Just need to pull it up the right way. So I'm going to shrink that heat shrink tubing down in there, and then we'll get to soldering in that box. We've got our entire cassette cable and board wired up here. Let's zoom in on the board. Ooh, blurry. There we go. Just the right amount of zoomification. So you might just be able to tell here that we have some little red looking wires. This is some solder through magnet wire. That's where I got this. I bought this from eBay, from this techfix.com. This is 30 gauge. I have some that's a little smaller than that. It's nice because it's insulated, but you can solder right through it, so you don't have to try to scrape the enamel off of it. So you can see on the switch here that I've got some wires soldered directly to the switch leads here. And what I did there, I just took, like a 3 or 4 inch piece of the wire, and I folded it in half and twisted it, soldered that to there so I could run one to where the wire came in from this cable, and the other over here to the remote socket. So in this position, these contacts aren't shorted out, so it relies on the remote signal from the development board, and you go like that, and it shorts these out, which shorts this out, and your cassette player will go. So if you want to fast forward and reverse and get your tape in the right position, you just go like that, and then when you got it positioned, you put it back in the computer controlled mode like that. On the bottom, we've got a similar situation. We've got the cable coming in. I took a piece of like 24 gauge telephone wire and wrapped it around there to act as a strainer leaf, kind of splayed out all the leads like this, so the green and the black go to the remote, and then we've got the braid here ground, which goes up here, and that goes across to all the grounds, and the red and white, which goes to the connectors there. And I have been testing this. It does save to the cassette just fine. It does not load, and we'll get into figuring out why that is in just a minute. Oh, and then I also took some E6000 glue and put dabs of it on the enameled wire and on our leads coming in here, right here at the strainer leaf, and did the same thing on the top so those don't flop around. So that should make a nice solid board for many years. So as I mentioned, we can save to our tape deck here. The relay turns on and off like it should. We can't load. We get the sound back in here on our white wire. From here, it goes to this dual op amp here at U38. The final output of U38 jumps over here to U36, which is a line receiver. And that'll take it, this runs on plus and minus 12, and this will take that and convert it to 5 volts that the processor can understand. So we're losing the plot somewhere along the way. There we go. Okay, now I've already taken some screenshots from the scope, and I'll cut them in here as we go along. So first we're going to test here at P2-6, which is the big white connector. And you can see we've got a good looking signal there. We test at U38 pin 2. We've got a signal there. The output of this first stage is pin 1, goes over to pin 5. We got the same signal at both these locations, which looks like this. And by the way, this looks kind of interesting having these two diodes back to back, and after puzzling on this for a while, I'm pretty sure that that's just clipping the signal, so it's either, it's 0.6 volts either polarity, and it won't be different than that across this stage. So we've got the input at pin 5, and as you can see, we have nothing here on pin 7. I wanted to make sure that, this input on U36 wasn't bad in pulling this down. So I pulled U36, I bent the pin out, didn't make any difference. I also put a socket on U38, and I checked, R40 and R41 here. R40's 12K, R41's 1K. Those are just fine. So it kind of seems that U38 might be bad. And I noticed with U38 in circuit that the measurement we were getting on R40 here was kind of low, which I thought was odd. So we'll go ahead and pop in a new R40, or excuse me, a new U38, and we'll see what happens. So let me get a super sophisticated chip removal tool here. Oops. Let me remove the power from the board first. Gosh, what was I thinking? I was so busy yakking, I wasn't paying attention. Okay. Original chip. Replacement chip. Let me bend the legs in a little bit. So you just take the chip and go like that on a hard surface and You can bend the legs in a little bit. Get the required old man glasses here. Or if you prefer, the glasses of experience. Pop in our chip there. I've still got over here, I've got pin 4 on U36 pulled up. Okay, conveniently there is a ground right on this cap right there. And we can go at pin 5 on U38. Make sure we're getting the signal there. Okay. Going to tell it to load. It doesn't matter, we're not at the start of the RAM that I saved. I just saved the whole batch of RAM. You notice I've got all 4 RAMs in there. I just saved that whole section of RAM out to the tape, so we had a nice long section of tape to test with. HIJKL. Okay, the cassette is moving. Okay, so now we're going to measure at pin 5. Okay, we've got a signal there. And we'll measure at pin 6. And we've got a signal there. And I don't think we did before. I didn't show that, but I don't think we did. And we'll measure at pin 7, and looky there, we've got a nice big signal. Okay, so we're still not loading anything because I've got pin 4 pulled up on U36, so we'll fix that, and we'll go back to the original program I saved. I saved that little type-in example program that added a couple numbers, and we'll try loading that and see if it does anything different. That's nice and small. Okay, so we're all set up now. The cassette deck is right here off the screen, so what should happen is I'll hit return to take it out of kind of this mode where it's just been initialized, and I'll hit L. That'll start the cassette deck, and when it finds the program and start loading, we should see the shift LED here blink. So I'm going to hit return and L. Cassette deck is running. Look, you might just be able to see that the shift light is lit up. Hard to see on camera. Oh, it beep, 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 beeped. And it says test, which is the name of the program. It shut the cassette deck off. And I think I hit return from here. And no, I don't know what that did. I thought it would run the program after that, but it didn't. So, so we're able to save and load the cassette, and the problem was just that op amp chip there, which is an RC4558. Luckily, I was able to scrounge one of those up. So we have bulk saving to cassette working. Oh, as you can see, that little hand-wired board is back in the case. I had to redo the case a little bit to make room for where I soldered the wires on toward this end. So this side is the new version, and I'm printing this side now. You might be able to hear the 3D printer behind me. And then that'll all be done. I guess now we can work on, well, either the serial port or the ROMs. I think we might do the serial port first, because if we get into getting the ROMs figured out so we can use EPROMs for University Basic, then we'll want the serial port working at that time. Alrighty, now to get our RS-232 working here. So it had this jumper wire on there, which was, I got notes here somewhere, across pins 7 and 20, which was just grounding out DTR. That was probably whatever they had it hooked to required that, so I took it off. We didn't require that. It was a little frustrating trying to look this up in the manual because I had to go to 3 different places to find out enough information. So it had this in section 2.6, giving you kind of like a general overview of how it works, but it doesn't tell you well, it says the baud rate's either 110 or 300, depending on when you reset this thing and it says CPU ready here. If you hit A through Z, it'll switch to 300 baud through the RS-232, and if you hit 0 through 9, it switches to 110 baud. 110 baud, so you can connect it to a teletype. It does have the capability to do a current loop for a teletype. And the next thing you come across in the manual in the appendix is the wiring diagram of the port. That looked pretty standard. I find this in the back, which is how it's wired. It's a standard DCE, like modem wiring to a terminal wiring. But it doesn't say anywhere in the manual, what the parameters are. Is it 8N1, 7N1, even parity, odd parity, 7 data bits, 8 data bits, that type of thing. A little bit frustrating. I thought it might be 7 data bits because it was designed, they talk about actually hooking it to a terminal. So at any rate, the first thing I did was plug this into a real hardware serial port that's on my PC, and I'll pop the picture up here. I was just getting a constant stream of zeros out. So then I measured, now I don't have the probe hooked up, but I'll pop the picture up here on the screen. I measured the output pin, pin 3, and it wasn't actually outputting anything. That was rather odd. So how am I getting an output, to my serial card on the computer with no actual output coming from here? Maybe it was a signal leveling thing. Maybe my serial port on the computer was a little wonky. So then I switched, I plugged my FTDI USB to serial converter in here, and it didn't get that. Maybe it's a difference in signaling level between the two, something like that. Didn't know. But at least it wasn't a constant stream of zeros. So now that I had a connection, I'm in reset mode here. I hit A. You can hear it beep. So it's doing something. And if I go over to the terminal, or, cool term, and I hit, well, I'll just hit A. It doesn't matter. I'll just hit a letter. This beeps. It's receiving something. And indeed, if I check the signal that's being received, it was receiving something. And I thought, well, if it's receiving something, it might be trying to transmit something back. And let me zoom in here so we can see the schematic. So this is our transmit line right here. And it goes straight out for RS-232, and it branches down to go to this optional current loop stuff for a teletype. This goes through a NAND gate here on U37, which is a line driver. And that just means it takes 5 volts input, and it'll give you plus or minus 12 volts output. And so I measured at the output, which is pin 2 of the TMS 9902, the RS-232 chip, to pin 13 on U37, which I'll pop up here. And indeed, when I was hitting a key on the keyboard, this board was trying to respond. And I was seeing data here on this gate of U37. This other input just here is tied high. In static mode, without transmitting anything, both of these inputs were high. This is a NAND gate, so the output should have been low, but the output was indeed high. So that can't happen. That points to a bad U37. This is an MC 1488. It's the same type of chip used on the Model 100. It's the same type of configuration on the Model 100. You have a line, oops, zoom out. You have a line driver chip to get your plus or minus voltage output for RS-232 and a line receiver to convert that back into 5 volts. So this is the way it was done back in the day, and these chips are kind of delicate. They tend to go bad. So anyhow, this is pointing to a bad chip. I have some extras on hand. That equivalent TI part, the 75188, because I work on a lot of Model 100s. So we'll pop that in and see what difference it made. Okay, so I'm connected back to the hardware serial port. It functioned with the chip replaced with FTDI, but it wasn't quite right. But we were getting something to the screen. I wasn't sure if it was because of the USB adapter or if it was the settings. Switched back to the hardware serial port. And I've got this reset. If I hit A here, you see that we do get a question mark response. And if I hit M, oops, if I hit M, it's acting, it looks like it's acting right. And if I type in 200 for address 200, it's gobbledygook. And if we look at the hex view, we have this weird 8D0A. I was guessing that was supposed to be a 0D0A. So it looked like for some of these that the high bit was set when it shouldn't be. Was that the number of stop bits, the number of data bits? I don't know. So what I did then is went to 7 data bits. And if we hit enter now, we get our question mark prompt back, and I can do M200, and it'll show us what's in that address. And it's a 16-bit value because it's a 16-bit processor. And if we just hit space, it'll go down, by each 16-bit value there and show us what's in there. So we're communicating now over the RS-232 port. Not really a big deal. It was just the line driver that was bad. Weird initial symptom with getting all zeros with the hardware serial port on the PC. That was kind of an odd one, but not too difficult. Now we can look at replacing our EPROMs to get this cobbled up one out of here. And to be able to run UniBASIC, we need to program an EPROM and pop them in both these slots. And of course, that's a little difficult. Let's get started on that now. So our goal now is to program some EPROMs for U33 and U32. These use different flavors of ROMs/EPROMs, of course. And being TI, they kind of did their own thing, which wasn't that uncommon back in the day. There wasn't as many standards for these things as we have now. So U33 originally was this guy, which was a 4732 masked ROM. We can see the pin out there. The EPROM equivalent of that is a 2532, which is a whole lot like a standard in the TMS 2532, very similar to 2532s made by other companies. There's only 3 pins that's different from a standard 2732. I didn't want to hack up the board though, and the owner of this did manage to find the correct EPROMs for this location. So I thought maybe we could program these by setting the programmer to a 2732 and swapping these pins around. And I did manage to get that to work once. You can see just here, we've got a nice 2532 with a new sticker on it that says U33 Unibug. I'm going to try to program another U33 here with the UniBASIC code for that location, and we'll see how that goes. The programmer's given me fits, so let's take a look at that. So the struggle of making these two ROMs. We started out with the Unibug ROM right here, which all the pins broke off of, and we had to do some surgery with the Dremel tool and soldered onto this carrier with some little tiny wires, but we got it to work. We're able to test out the Unibug ROM, make a copy of it with the using the back bit to dump it. everything was fine. Now this ROM is a 4732. That's a TI part, TMS 4732. 5-volt only, not too different from a lot of other things back in the day. A little different pinout than what we would think of a standard of like 2732 now, even though they're both 4K. So the EPROM equivalent of this is a 2532, which is made by TI, is the TMS 2532, made by some other people, and this footprint for the 2532s is not unique. Now, the problem is my programmer doesn't have a setting for 2532. It does for 2732, which is just the same thing essentially. And there's only 3 pins that are different. So looking at the pinout for the 2532 and the 2732, I came up with this table of pins that needed to be swapped around. And I built this, nice looking, high quality, very precise adapter. So we plug in our 2532 here, plug this into the EPROM programmer, and set it to a 2732 at 25 volts for the VPP, the programming voltage, and it should work. The owner of this board had sent me 5 2532 EPROMs, and the first one I plugged in, it came up with a overcurrent VPP error immediately. I'll post a picture of that up here. The second one programmed just fine, and that was, I made a new Unibug ROM right here, showing you the location and what's on it. So that was right there. I tested that. That worked fine. And I had 3 left, and all 3 of those would program the first 32 bytes, and then you would get a VPP overcurrent error again. And I tried programming a 2732, taking the adapter out, plugging in a 2732, which, looked at the data sheets and the VPP current is the same between the 2532 and the 2732. 2732 programmed fine. So the problem was I had 4 out of 5 of the 2532s were bad, all in a similar way. Well, it's not the first time I've seen that, the VPP overcurrent or the device overcurrent error with a bad EPROM. So I scrounged up some more locally. First one I plugged in, same overcurrent error. Second one, just programmed just fine. I got this UniBASIC done. So, yeah, a lot of these EPROMs are going on 50 years old now. They're failing. I had that problem with the 2708s with the LNW80. I had about 30% of those that had failed. So it's not surprising. It's just awfully frustrating. So, plugging in a 2532 here, that's a direct plug-in. You need a little bit of an adapter. I did find a 2732 or 2732 to 2532 adapter board. I'll put the link to that in the description below. I've got some of those on order, and it's set up so depending on where you put the socket and where you put the pins to go down, you can adapt it from one to the other. So I can put one of those together, set up to be 2732 on the bottom, 2532 on the top to make a proper programming adapter and get rid of this mess. And putting it together the other way, I'll send one along with this back to the user, and if he wants to program something different using a regular 2732, that'll pop right into there. This one, U32. Okay, this is even more complicated. Originally, this was set up for a TMS 2708 EPROM, which takes 12 volts and minus 5 volts and 5 volts, and is a different pin configuration than most things. And for the UniBASIC, you needed to change that to a TMS 2716, which requires cutting some traces on the board and adding some jumper wires. So the owner tried to order some of these, and what he got sent was regular 2716s. And these also require, a regular 2716 requires a 25 volt programmer. So I got to looking at the difference in pinout between the TMS 2716 and a normal 2716. And once again, there were only 3 pins that were different. So I thought, well, maybe since to put the the TMS 2716 in, you have to cut traces and add jumpers. It wouldn't be that big a deal to cut traces and add jumpers to add a regular 2716. And indeed, there was only a few things that you needed to do. Let's see if I can show you the schematic here. So here's where we would have cut and jumpered to put the TMS 2716 in. And for the normal 2716, we can leave this all where it was. And we're just going to cut the -5 volts going to pin 21. We're going to cut the 12 volts going to pin 19. We're going to jumper pin 21 and 24, which is just 5 volts going to VPP. And then we're going to jump E42 over to pin 19 where the 12 volts was. And that is address line 3 on the schematic. The address lines from the bus don't match up with on the EPROM, but it works. To modify the board to use a regular 2732 here instead of the 2532, it would have been a mess. It wasn't nearly as nice as doing it for the E32. So here's the modifications here. There's just a couple cuts and 3 little jumper wires. I used that enameled magnet wire that you can solder through. So this was the -5 volt line. It went up or down through here. This was the via that took it over to the chip that was here originally. So I cut on each side of that, add this little horseshoe jumper here, and then I'm bringing the signal from this E42 jumper up to here, that type of thing. That works fine. It looks nice. Easily reversible if you want to do that. It's as neat and easily reversible as the factory modifications to use the TMS 2716. And there is another jumper right here, E49 to E50, that you have to put in. That is shown right here on the schematic. That is just adding another line to the chip select. So that is it. And oops, whiteify. There we go. So we're finally able to burn the EPROMs we needed for University Basic. Got them both plugged in there. Got all the jumpers like it should. And I'm still trying to learn how to use it. Once I get an idea how to use it, then we'll finish off this video showing BASIC in action. Ooh, exciting. Okay, here's a wide shot of our test setup for testing the University BASIC. We've got the development board here, power supply, our cassette interface cable, and our cassette drive. And we've got the University BASIC ROMs plugged in here. Now I'm going to zoom in here on the keypad so we can see that, and then we'll get started. So I've powered up the board. I hit the load switch to reset it, and it comes up and says ready. And, I tried then typing on the terminal, and it did nothing. And luckily, I found the University BASIC manual and eventually figured out how to use it. So, surprisingly, you can use this in programming BASIC right through this calculator keypad thing. So if I hit return here, this is a basic entry mode. You might just be able to see the blinking cursor there. So I can do something like 10 PRI in print shift quotes high shift quotes return 20 go to 10. It is hard getting used to this keypad. So we just entered a short basic program, and we can type Where's the R? R, U, N, return. And it's repeatedly writing hi to our screen there. Pretty nifty. Now, I think it would be quite painful to enter any programs of any length through this calculator keypad, but they did a pretty good job making use of the 7-segment display for text and everything like that. So I'm going to hit the load button again to reset it. We go back to ready, return, and now I want to program over the terminal connection. So I'm going to type in the keyword unit, U, N. That gives me an error. U, N, I, T. Some of the keys are jumpy like that. It's getting better the more the keypad's used. And Unit 2 sets it to 300 baud. There's a list in the manual I'll pop up here. Why they called this command unit, I have no idea. Seems bizarre to me, so we'll go Unit 2. Return. And we still have our blinking cursor here. And we'll look at the terminal window now, and I'll type something like, make sure caps lock is on. Notice I'm typing on the computer, but it's beeping over here. And we get our listing on the computer. Now this is only 300 baud. We can run this up to 19.2 it says, but this is fine for right now. And if we run this program, note that it's displaying here and on the terminal window. Very interesting. And the only way I can find to break a continuous loop like this is to hit the load button to reset it. And you notice we just get the blinking cursor here, but we get ready on the terminal window. And you can also load and save to cassette. So here's a program I've prepared earlier, as they would say on the cooking shows. So make sure I got the cassette interface set to automatic. I've got the tape in the correct place. I will hit play and show you there's nothing up my sleeve. I'm going to type new. We have erased our super fancy basic program, and now we're going to type in load tone, and this should load a program off a cassette. And you notice we got the same thing here on our LED. Pretty neat. And you heard the relay click. The tape deck is running. Yep, I think we missed it. Let's try that again. Ah, there we go. I think the tape counter was just a little off. I started a little sooner, and that worked fine. So now we clicked off, we've got our cursor back, we've got the ready prompt here. We can type in list. And we have a program here. Now watch this and listen. So pretty cool that they made a tone command for the Piezo speaker there. And as I understand it, there was also an option for this so that you could get a color video output board. And there's actually some commands in BASIC for writing to the video board, displaying stuff on screen. That's pretty cool. So it seems like we've got everything working on this board. We don't have any peripherals that plug in over here to test this out, but there's just a few buffer chips in here. So I imagine all that would work. It's a pretty cool little board. A nice development system for a 16-bit processor from, about 1980. Managed to get it all working. finally managed to program some EPROMs. Pretty neat setup. So we've got our TI TM990-189 development board functional again. We're able to get some EPROMs built, test the UniBASIC, save and load to cassette. This is a pretty interesting board. It really surprised me. The manual is so-so. They left stuff out. There's information about one subject scattered all over the manual, making it hard to follow. How to get the terminal working in BASIC was kind of hidden in there. It was like mentioned as an afterthought and kind of strange. Anyhow, the board itself is rather cool though. An interesting idea TI had back in the day using this calculator keypad. It did provide some good functionality, albeit a little difficult to learn how to program on this keypad, but you know, if you were a university student in 1980, this would have been the coolest thing ever. So I hope you like this. I think the owner of this board is going to be excited to be able to have this to develop with. I think he will remember this from his university days. And now it's working again. If you have any questions or comments, let me know in the comment section down below. Would love to hear from you. Thanks to everyone who helped support the Hey Birt channel through Patreon and other means. It's greatly appreciated. I don't know if this will be my last video of 2025, but if it is, let me say Happy New Year, Merry Christmas, and we'll see you next year. Bye.